Hello everyone, this is the second part of the question paper solving for ET3112. So let's do question number 3. List 4 applications of image segmentation. There are so many applications and some of them are isolating pixels corresponding to an object or a region, example a drivable road in an image. Demarcating tumors in medical images, for demarcating boundaries of cells, for measuring the size of an organ, example a prostate. So for example, taking a flower cut out of an image and placing it somewhere else in Photoshop like processing and so on. So those are the applications. Part B, it is possible to find the threshold value automatically when segmenting an image with a bimodal histogram. Figure Q3b1 shows an image to be segmented using thresholding. Figure Q3b2 shows the histogram. Select a suitable threshold by observation, state the threshold value and justify. So when you look at the histogram, you can see there are two modes. So these correspond to dark pixels, these correspond to bright pixels. So you can see in a very dark background, this must be a bright object. So you can take the middle of the bright region, maybe like 12, and middle of the dark region maybe like 1, and you can pick the value in the middle. 1 plus 12 divided by 2, that's 6.5. so approximately take 7 as a threshold. So this is 7. Segment the image using this threshold. So now we have to segment the image over here using that threshold. Threshold is 7. So anything above 7 is segmented as the object. So 12, 14. So let's use the highlighter for that. All these images, all these pixels get segmented. Because they are greater than the threshold value that we picked, which is 7. So you can see what is expected is being achieved through this by selecting that threshold. Actually, the outsource algorithm, which is not of a concern in this question, does that computation of finding the threshold in a bimodal histogram. But the problem in this is you can see this isolated region which is above 7 also gets segmented. So this is the answer to the second part. The problem is non-contiguous regions get segmented in this. So I accepted 6, 7 or 8 as the answer for the threshold, and segmentation is noisy or non-congruent or non-contiguous. So some answer like that. Is acceptable. Then we can move to part C. Segment the image in figure Q3C using region groving. Using the threshold, using the shaded pixel at 710 with the value 15 as a seed, and the threshold is 2.1. So remember T or the threshold is 2.1. So seed has been highlighted. So T is 2.1. So what is the algorithm? If the pixel of concern, if this is P, if this pixel is P, intensity of that pixel minus the intensity of Q, a neighboring pixel. If it is less than T, we put that in the segmentation. So let's consider these 4 pixels, the neighbors, 4 neighborhood. So 15 minus 13, the absolute value is less than 2.1. So they get segmented. Then take each one of them in the boundary and see their neighbors. So 13. So let's take the neighbors of this pixel. So 13, 13, 13. They all do not have a difference more than 2.1, therefore they all get segmented. Then let's take this pixel, is 13, and consider its neighbors. 12 is the only neighbor that we have not considered, that gets into the segmentation. Now let's consider this pixel to the left of 15 and consider its neighbors. 13, we consider only the 4 neighborhood, that is the difference is less than 2.1, that gets segmented. Let's consider this pixel. Not a bit service, so this also we get segmented. You cannot see the value of that. So you can see the frontier is propagating so slowly, and they get absorbed into the segmentation. So now I will just highlight them so you can see, because 2.1 less than 2.1 thing all get absorbed, and the difference to the adjacent pixel is less than 2.1, all get absorbed the segmentation. So all these things get yes. So through 12, this 10 would also get into the segmentation. This is not the way the frontier will progress, but I will just highlight them. They all get into segmentation, but you can see this range does not get segmented. So therefore the leaks, if there are no leaks, the region growing produces a congruent region as usually as expected. So figure Q3D, question number part D. Figure Q3D shows a 3x4 image. Carry out one iteration of k-means clustering in the intensity space. Use Manhattan distance. Manhattan distance is just the absolute value between differences, and k equals 2. Select 0, 3 and 2, 0 as initial cluster centers. So 0, 3, 0, 3. Let's take this as the red cluster center. And then 2, 0, this as the green cluster center. So now we have to see the distances of each of these pixels to the green one and the red one, and then do the clustering. Let's consider all the pixels. So we have the pixel 0, 0, then 0, 1, 0, 2, of course 0, 3 is in the red cluster, 1, 0, 1, 1, 1, 2 and 1, 3. Then 2, 0 is already in the green cluster, 2, 1, 2, 2 and 2, 3. So I want to see whether they are in the green cluster or the red cluster. Yeah. So for that I need to write the distance. Manhattan distance is just subtract the individual coordinates and write. So for example, let's consider 120. 100 for the 120 this pixel, you will get 10 minus 120. This is 110. For 0, 1, 190. For 0, 2, 230. For 1, 0, 40. For 1, 1, 50, for 1 2, 90, for 1 3, 110, for 2 1, 30, for 2 2, 10, for 2 3, 20. Now let's consider with the red one. Red one has 50, so 10 minus 50 is 70, 200 minus 50 is 150, 240 minus 50 is 190, 0, 10, 50, 70, 10. You get the absolute value. That's why I'm writing positive as 10, then 30 and 20. For 2 2 it's 30 and 20. So we had to pick the larger ones and then color. This red, smaller, 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 smaller. So 2 2 and 2 3 are green. Two one is yeah. So all others are red. Okay. Now that's using Manhattan distance with only a color, only in the intensity space. Now if we do the k-means clustering using intensity space and spatial space, scale the spatial space by 100, then the result will be different. Let's do that also. So let me erase this. Okay, let's take 0 0. So this one is once again green, this one is red. Let's take 0 0. The pixel intensity difference is 110 plus, and then you have a Manhattan distance of 1 and 2, that multiplied by 100 is 200. And then let's consider with the red one the same one. So the intensity difference is 70 plus the pixels is 1 2 3 plus 300. So therefore here you would get 310, here you get 370, so this becomes a green pixel. For the pixel 0 1, 200, 190, Manhattan distance would be 1 2 3 plus 300. The shortest, we'll have to get the shortest one, of course. For the red cluster, the intensity difference is 150 plus 200. So we can see 350 versus 490, so that becomes a red cluster pixel. 240 would obviously become a red clustered pixel. I think let's do that calculation again. 240, 10 minus 240, 230 plus Manhattan distance will be 1, 2, 3, 4 plus 400. For the 50 it will be 190 plus 100. That's a red one. So you can see, you can quickly do this. So this is 1 0 50, that's 40 plus 100. This one it's 0 plus 1 2 3 4 400 Manhattan distance 400, so therefore that becomes a green pixel. 60 also becomes a green pixel. 200 plus 10, this is 10 plus 60, 200 plus 50, this is 10 plus 300, that becomes a green pixel. 100, 90 plus 1 2 3 300, and for the 50 its Manhattan distance is 2, so 50 plus 200. Manhattan distance means you have to walk in paths like that, so obviously that is a pixel with red. This will also be red. So let's take the 40 pixel number 42 0, sorry 2 1 1 3, did you do? Yes, 2 1 10 plus 100. So you don't have to worry about this number, you can directly write it as green. This will also be green, and this will be the last one. Let's write 2 3, that would be 10 plus 1 2 3 300. This one 20 plus 1 2 200, so that becomes a red. So you can see the segmentation is quite nice in this case when we consider the spatial contribution also, but you have to clearly see that it has to be multiplied by some number to match the contribution from the intensity space and the distance space. So here you can see they are not even contiguous in the previous case. Okay, so now we solved that problem. Let's move to question number 4. State 4 vision tasks for which machine learning or deep learning is extensively used: image classification, object detection, semantic segmentation, instance segmentation, depth estimation, surface normal estimation, panoptic segmentation, and so on tasks. So you can write things like autonomous driving, like that, very large scale tasks also. Okay, next question. Corner detection is the first step in many conventional computer vision algorithms. It computes a cornerness measure. Figure Q4b shows a portion of values of cornerness measure. So directly the cornerness measure R is being shown here of an image. State an expression for the cornerness measure used in Harris corner detector. So that you have to write by memory. So R equals determinant of M alpha times trace squared M, where alpha is equal to 0.04. M is the second moment matrix. State an expression for the cornerness measure used in the Harris corner detector. That's what it wrote. Identify the location of the corner. So we have to maximize R. So highest R value is here. So this is 0 1 0 1 2 3. So this is pixel number 1 1 with R equals 0.0225. is the corner. State how to identify a corner in scale covariant manner. So you know that cornerness measure depends on the scale. So you have to build the so-called scale space and maximize R over the scale axis also. So here we maximized over this axis and that axis. And then you have to have the scale axis also and maximize it over the scale axis as well. Okay. Then part C, consider a data set of three classes of images, say dogs, cats and bunnies. Dogs, cats and bunnies, as an image is represented by a four-dimensional vector. Usually images are represented by much larger dimensional vectors, maybe like 32 by 32 times 3 vectors for the three colors, but here we are considering using four vectors. So somehow you extract features and make it into 4 vectors. Let's say a linear classifier after the learning process is represented by a W equals this one and the B bias. So there are 3 classes, right? Class 1, 2 and 3. So as a result, you have your W is 3 because there are 4 features, it has 4 numbers. This 4 corresponds to the feature dimension. This 3 corresponds to the number of classes. Because of the number of classes, B also has B is also 3 by 1. Okay, the first row is W and B is 1 versus all classified dogs, the second for cats and the third for bunnies and so on. State the steps for representing an image with such 4-dimensional feature vector. So in this case, you have to write the bag of visual word steps. First you have to compute the features. Select K as 4, that means the dictionary size or the vocabulary size. We do K-means clustering. Pick the means. So we do K-means clustering and pick the means, and that is a visual vocabulary. Get the histogram. So this bag of visual words process has to be described in this case. Okay. So if you do not understand this part, please read about bag of visual words steps. How do you get the class scores? You get them by y equals wx plus b. So now here we are given that image, a particular image has a vector 3, minus 1.5, 1.6, 8.1. Of course, it is 4-dimensional. There are 4 numbers in this vector, so you have to write y hat is wx plus b. What this means is minus 0.4, 0.5, minus 0.3, 0.6, 0.4, 0.5, minus 0.2, minus 0.6, 0.5, minus 0.3, 0.8, minus 0.6. This matrix we multiply by the given image, 0.3, minus 1.5, 1.6, 8.1, and this is a 3 by 4 matrix. This is a 4 by 1 vector, so you get a 3 by 1 vector here. So this is 3 by 1, so that we add b is 0.2, 5.2 and 3.2. So when you do that multiplication and addition, you get 3.71 minus 0.61, 0.22. So this is the highest. So therefore it is the first class of the dog class. Okay. Then let's go to part D, the last part. Consider neural network implementation for character recognition. There are 52 characters from A to Z, lowercase and uppercase. So 26 for lowercase, 26 for uppercase. Assume that each character is 30 by 32 by 32 grayscale. The network flattens the input first. So therefore each vector that we get at the beginning is 32 by 32. That means I think it's 1024. sketch the network, compute, okay, then the network flattens the input first. There is a dense layer of 120 nodes and dense softmax output layer. So you have 1, 2 up until 1024 and 1, 2 up until 128 nodes. So this is dense. So each one is connected to each one of them. And then softmax 52 because there are 52 characters. That's the sketch you are required to draw. Compute the number of learnable parameters in this network. Okay, how many nodes must be there in the softmax layer? 52. So yeah, I forgot to say that. So learnable parameters, so here you have 1024 times 128 weights, and then each one of them will have bias plus 128 plus then 128 times 52 plus you can say there's a bias for each. This is the answer for that. So I think you get this number. This part is is correct. Okay, then if the network is altered to have first a convolution array of 3 by 3 convolutions with 64 filters, followed by max pooling layer of 2 by 2 pooling window, and then aforementioned dense network, compute the number of learnable parameters. So the stride is not set, so here you have to assume that the stride is 2 for 2 by 2 pooling. Convolution and so output size is this. So learnable parameters. So it's the image is 32 by 32. So there are 64 convolutional filters. So 3 by 3, 64. Each of them will have a bias of 64. So 640 is what you get from here. And then max pooling has no learnable parameters. The network size becomes 15 by 15 times 64. And then it says then aforementioned dense network. So then flatten. So this would be 15 times 15 times 64 would be the length of the vector. $14,400 will be connected to 128. So there are 1,843,328. So this you get by 14,400 multiplied by 128 plus 128. So finally, this one I think you know how to compute. Previously also we computed. When you add all of them, you get this. Okay, that's the end. Thank you and good luck.